Hello everyone, welcome to our first question in the design for Shear section. And in the first question, let's go over briefly what is given to us and what is required to find in the problem. So the given problem is a simply supported flanged beam. The base width on the larger side is 750 millimeters. The width on the smaller size is 250 millimeters. The length is 10 meters. We are using C25 concrete, which means that the design strength is 17 megapascals and the tensile design strength is 1.2 megapascals. And also we are using an S420 steel, which we're going to use both in the longitudinal bars and at the shear reinforcement, which means the yield design and the yield web design will be equal to each other with a value of 365 megapascals. So in this question, we're going to find the amount of shear reinforcement that is needed and adequate to support the structure. Okay, let's start the solution to the problem with following some estimations in the preliminary design stage. So, okay, I'm writing preliminary design. So at the preliminary design stage, we are conducting this procedure to find the age, the depth of the cross section, because in the question it is not given to us. So we are going to assume a live load and a dead load. So just at the preliminary design stage, let's estimate the dead load as 20 kilonewton per meter and the live load as 10 kilonewton per meter. So the distributed load, which we are going to nominate and show with PD, is 1.4 times G plus 1.6 times Q. So it is 1.4 times G, which is 20, and plus 1.6 times Q, which is 10. So when we do the calculation, 1.4 times 20 plus 1.6 times 10, we get, let me check my calculation, 44 kilonewton per meter. And what is the critical design shear? Actually, in this case, we're going to use the very simple statics formula, PD times L over 2, to find the axial load, the shear load acting on the cross section. So PD is 44, so L is 10, which is given in the question. So our PVD then becomes 220 kilonewtons. Since this is a flange section, the shear will govern the equations, and because of that we need to use the formula that I'm going to show right now to find the depth, the D. So what is this formula? As we have covered in the lecture notes, it is BW times D equals to 0.9 times VD divided by FCTD. So this is the formula that we need to use. So BW in our case is given as 250. We don't know the D value, and we also know the VCTD as 1.2. So let's plug in those numbers in the equation here. BW, which is 250 times D equals to 0.9 times VD, 220 divided by 1.2 megapascals. And when you arrange the the dimensions and the units, you will end up with a D value of 660 millimeters. Okay, the D is 660 millimeters. And in that case, I'm taking the clear cover as 40 millimeters, which means that the total height of the cross section then becomes 660 plus 40, which becomes equal to 700 millimeters. That is what we've done in the preliminary design stage, and let's move on to the final design. So, final design. We are doing the final design to get the exact figures for the shear reinforcement that we need for the given structure. So in the final design, I'm going to use a different live and